So today what we're going to do is we're going to talk about the ideal gas law. And with the ideal gas law, what makes this a little bit different is that it's not two different situations. So if you think about the types of problems that we've done up until this point, we've said, hey, what if it's this pressure and volume in this situation, and we change the pressure, what's our new volume? So we had two different situations. Well, with this, we're going to see that what we've got is we're going to calculate a condition when no conditions change. So we're just going to have one pressure, one volume, one number of moles, and one set temperature. And then there's also the gas constant. And so that's what we'll learn about here. And that gas constant that we've got is a value known as 0.08205, and the units that we would use for this would be atmospheres times liters over mole Kelvin. So if you remember on last notes, we said it's great to set up these things, these gas laws, by using gas law ratios, but if you want to plug and chug and just use a formula, fine, you're welcome to. It's going to be the same thing here, but just remember your units have to be in these units in order to use the gas law constant, so that just means you need to make sure that you convert those right up front if you're not using dimensional analysis. As always, we know that we've got to work in Kelvin on these. Okay, so I'm going to go ahead and do the dimensional analysis direction because I'm pretty sure that you guys know how to plug and chug numbers in there and just solve for some different things. Okay, so there was just a question, do we have to memorize the gas constant? And I'm going to go with yes. You might occasionally see it given to you, but let's say that you should memorize it. And again, if you use it enough, then you're going to see that it comes pretty easily. Okay, so our first example problem. Actually, let me go back to the idea that I'm gonna do this using dimensional analysis. And what that means is that this is a constant that I'm always going to have thrown into a gas law problem, also known sometimes as a Pivnert problem, because of our formula, if you think about what that formula is. So since I'm going to use that in every single one, I want to make sure all of those units cancel out except for the variable that I'm trying to solve for. So for example, when it says find the temperature, I know that I'm going to want everything to cancel out except for Kelvin. Well, if I want Kelvin to be what I'm looking for, do you think I want to start with this as is, or do I want to flip those, the numerator and denominator? What do you think? Flip, right? Because I'm solving for Kelvin. If I'm trying to solve for Kelvin, I want that to be in the numerator. That's what I want. So this is an approach using dimensional analysis. So what I'm going to say here, maybe I'll make myself a little note that I'm looking for Kelvin. So I'm going to start by saying mole Kelvin divided by 0.08205 atmospheres liters. So now, do I have to try and do any algebra and figure out, well, am I going to divide by P or V or T, or what am I going to multiply by? No, all I'm going to do is try and make my units cancel out to where I'm just left with Kelvin. So that's my goal, is to get everything to cancel out except for Kelvin. So now I read through here. And by the way, don't let that trick you. Yeah, it's asking for it in degrees Celsius, but you must work in Kelvin. That very last little step you can convert to Celsius again. Okay, so I see that I've got 0.6, how many babies there? 0.667 moles. So if we've got moles, what do you think? Where should we put moles so that it cancels out, top or bottom? Bottom. And it's 0.667. All right, getting closer. And it's in a 4,890 milliliter container. Well, I know that milliliters is not what I want. I feel pretty confident with my ability to convert things like this metric right now. What do you want to call that instead? Good. And I always want to double check and make sure you guys are moving that the right number. So there's 1,000 milliliters in a liter. So when I put my liters down there, hopefully you guys can look at that and say, yep, that needs to be in the top so that it cancels? Well, I'm getting much closer, and it tells me that it's going to exert a pressure of 2470 torr. Well, I've got atmospheres down here, so I've got pressure in the denominator, meaning I need to put pressure in the numerator in order to make that cancel. Well, those don't cancel, torr and atmosphere. Let's make them cancel. There's torr, there's atmospheres. So we just have to think about our conversion factors that we know, and hopefully you guys have these memorized also. So we know that 1 atmosphere is exactly the same thing as 760 torr. So now everything cancels out beautifully except for Kelvin, which is what we were looking for. Does it really matter where I put these numerator and denominator things? As long as they're in the numerator and as long as they're in the denominator, that's all we need. If these blank spaces bug you, you can always throw a 1 in there. But it doesn't really matter as long as you get your units to cancel. Okay, I hear lots of calculators. So let's keep calculating, and if you get the answer, just yell it out. 290, that's what I got to. So 290 Kelvin. If we're thinking about sig figs, it is those 3 sig figs right there, 290 Kelvin. So that's not the question. The question says, what is it in degrees Celsius? So what do you have to do? Subtract, and it's that number that you guys all know, the minus 273, and that's going to give us 17 degrees Celsius. Okay, again, I want to throw out the idea to you that this is your formula. We were solving for this. If you want to throw things in there and just use algebra, you guys are welcome to do that. Would you necessarily catch the fact that your pressures were not in the right units? Maybe you'd convert that up front. Up to you. But if you want to do that, as long as you're showing all your numbers and all your units, you're welcome to. But you're going to see me work them out with dimensional analysis. Okay, so here's another sig fig question, and this is the common question that comes up when we start. We're pretty comfortable now, I think everybody is, with multiplication and division. But now what happens is we've got this value, which is just a constant, and we've got this value. Well, when you subtract, when you add or subtract, your rules are to round to the least number of digits past the decimal. Well, you don't have any digits past the decimal. You don't have any digits past the decimal. So you round to where you don't have any digits past the decimal. And that's really, a lot of people have questions about that because we don't do a whole lot of addition and subtraction with our calculations. Okay, next one. Hopefully you guys felt good with that. So I'm remembering my gas constant. Here it is. And the question is, what's going to be the volume? So obviously, I'm going to be solving for that guy. You look at that and you see, yeah, it's already in the numerator, so that's where I want to keep it. So let's start with 0.08205. I don't know why. I always write my atmospheres first. Doesn't matter. It's just my habit. Atmospheres, liters over mole Kelvin. So we've got all those units there. We just want to play the game where we make them all cancel out except for that guy. So here we go. We have 18.6 grams of argon. Ooh, grams is not going to cancel out. Grams, what might we be able to get that to cancel out with eventually? Moles. Good. So that's an amount, just like moles is an amount. So if I've got moles on the bottom here, I want to cancel it out with the stuff on the top, right? It's obviously not canceling out yet, but let's get it to cancel out. We know that we've got 18.6 grams of argon. So when we look at our periodic table, we see that for every 1 mole of argon, we have 30, thank you. Is it 9.4 or 9.5? I have 9.5 written down. 9.5, yeah. Okay, so 39.95 grams. So now by doing that, we got our grams to cancel and our moles to cancel. Again, it's just playing a canceling game. That's all we're trying to get them to do. It's 15 degrees Celsius. So should I plug 15 degrees Celsius up here? No, I was trying to fool these people. There's, yay, I've even got conversions going on. So that's 288K. So we know that we're going to plug in 288K in the numerator so that our Kelvin and our Kelvin cancel. Last one, I need to get my atmospheres to cancel, but doesn't look like it's going to happen right away. I've got atmospheres in the numerator, so it looks like I need to put my pressure in the denominator. So right down here, I'm going to say 735 torr. But again, that doesn't cancel. If you want, you know what, just for the sake of having space, I will put it right there. So I've got pressure in the numerator, pressure in the denominator. Now all I have to do is get them to cancel. So atmospheres needs to go down here, torr needs to go up here. 1 atmosphere, 760 torr. Everything cancels beautifully except the liters. And let's see what people come up with. I'm going to write it down. Let's see if they get this. Okay, am I right? Anybody else get that one? Okay, lots of head shaking. So 11.4 liters is what you should come up with on this. Okay, so moving on to our last ideal gas problem. I think we're going to have lots of time today to work on homework problems, which might be nice. So last ideal gas problem. In this question, it says, what will be the volume, that guy right there, of 32 grams of oxygen at STP? Anybody do those quick calculations in their head and come up with an answer yet? Oh, no takers on that. Let's see what we can come up with here. Okay, so we're going to start with our 32 grams of oxygen. All right. And you know what? I'm sorry. I should not have done that. I did not mean to do that. Let's always start with our factor that we have up there, our R. So we're going to go ahead and say the 0.08205 atmospheres, liters over mole Kelvin. Okay, so now what we're going to do is we're going to say the only thing that we really see that we've got given to us is 32 grams. What else do we have? T equals what? 273 Kelvin. What does your P equal? What would be the easiest P to use? 1 atmosphere. And remember the reason being that this guy is given to you in atmospheres up here. So that's going to be your easiest value. So now we can go through and say, okay, maybe we'll cancel out our T first. I've got Kelvin in the bottom, so let's put our Kelvin in the top and get those guys to cancel. I've got atmosphere in the top, so let's put our atmospheres in the bottom, get those guys to cancel. Where should I put my 32 grams, top or bottom?
Bottom. No, top.
Top. Yep. So I've got moles in the bottom, so I need my amount, my 32 grams, to go on the top, and that's of oxygen. Well, we can do that simple conversion, get rid of our grams and go to moles. 1 mole has a mass of 32 grams. That makes that math nice and easy. In fact, that cancels out also. So now our moles cancel out. What are we left with? Liters. And what is it? Anybody do it yet? Yeah, 22.4 liters. That looks familiar. Why is that?
Well, I was about to ask you, since it's a gas.
Uh-huh.
You
Okay, so catching on to that, knowing that this is a gas, and we're talking about gas laws, and the other part of that is this guy, right?
Yeah.
So 1 mole, and then being able to look at this because you've been in chemistry for a while, looking at that and knowing that that happens to be 1 mole of oxygen. So you've got 1 mole of oxygen gas at standard temperatures and pressures, well, yeah, 1 mole of any gas is going to have a volume of 22.4 liters. So that's what we end up seeing there. If you ever see STP, you are welcome. If you think about it, you are welcome to use this conversion. Be careful and make sure you're using it in the right situation. But you're welcome to do that. 1 mole of any gas at standard temperatures and pressures has a volume of 22.4 liters. All right. So I think, let me see, I think that's, you know what, let's just go through this process really quickly. You don't necessarily need to write this down. But if we were to just take this and solve for this, remember, this is something we use a lot when thinking about situational problems, just looking at this relationship right here, and that helps us think about the mathematical relationship between those different variables. But if we wanted to think about where the gas constant comes from, well, if you were to plug in pressure of 1 atmosphere and a volume of 22.4 liters, and this is divided by, if you're talking about 1 mole of a gas and at standard temperatures, I bet you're going to come up with that value. So that's where that magic number comes from. There is a relationship between those two guys. All right, that is going to be it for this half of the video. I think I'm going to have a different recording for the Graham's law.